Welcome everyone. In this video, we are going to solve a game theory type problem. It's like a game played between two people, Peter and Becky. So Peter will be saying an integer. It can be negative, it can be positive, it can be 0, and Becky will be writing it on the board. So for example, suppose Peter says 3, then Becky writes 3. But Becky can also write, instead of writing the number said by Peter, they can also write the sum of all the numbers written on the board along with the number said by Peter. Say for example, Peter says 3 first and Becky should write 3 because it's the very first number. Next Peter says 5, Becky writes 5, suppose. And in the next attempt, Peter let's say says minus 3. Now Becky doesn't want to write minus 3. So they can write 3 plus 5 plus minus 3, which gives us 5 in total. So the next number will be 5, and let's say Peter says 7 and Becky can write 7, so they proceed to write 7, and let's say Peter again says 7. Now Becky doesn't want to write 7 on the board, so they can write the sum of all the already written numbers along with the number uttered by Peter, which will be 10, 20, 27. So the next number will be 27. Likewise, the list written by Becky shall go on indefinitely. The question is, can Peter ensure or guarantee that a particular number n is written at least 10,000 times by Becky? So you should understand that Becky can deny writing a number and instead write the sum of all the numbers along with the number uttered by Peter. So maybe Becky can play cleverly and not write the number uttered by Peter, thereby avoiding the number said by Peter. But can Peter still ensure that a particular number n is written at least 10,000 times on the board by Becky? And in fact, find all such possible values for n that can be written 10,000 times by Becky guaranteedly. So that means Becky should not be able to escape from the process. First of all, you have to try some hit and trial, but let me give you a hint. You have to subdivide this into two cases, when n is odd and when n is even. Now, an even number can be written as many times as Peter requires. That's the logic. And when n is odd, then Becky can play around and not write n as many times as required. Maybe Becky may never write a number that is odd. So Becky may escape. So that means Peter cannot guarantee 10,000 times written number n. So well, how to justify this? How to prove that this is the case in fact? Let's assume the case is when n is odd. N equals some odd number. Let's say it's of the form 2k plus 1. Notice, Becky will be compelled to write the number n on the board if the sum of the previously written number equals 0. If and only if the sum of previously written number equals 0. The reason is that if the sum were 0, sum of all the previously written number were 0, and suppose Peter claims n, then Becky has to write the value n, or they have to add it with the sum of all the remaining numbers, which will again give you n. So therefore, Becky will be compelled to write n. So if Peter can ensure that the sum equals 0, the null sum occurs frequently or as many times as required, then definitely 10,000 such occurrences of n can be guaranteed. And we are going to prove that Becky will play around and try to escape from this. Scenario. Because if sum were not equal to 0, then clearly Becky can write the number plus the sum. So here is the algorithm that Becky will follow. Becky writes x, a number x. So suppose let's say the number uttered by, so x is the Peter's claim. Peter's claim. Then notice that Becky will write x if s plus x is not equal to 0 and x is not equal to n. So this ensures that the new sum is not equal to 0, neither the written number on the board is not n. And they will write s plus n if s plus x is not equal to, if s plus x is equal to 0 or x equals n. So here we assume that the initial sum is non-zero. So first assume that there are like as many zeros as claimed by Peter, and we are now working for numbers that are other than 0. So the very first number which is non-zero, the total sum will not be 0. Now if total sum is not 0, the new sum, this is x. If the initial sum is not 0, then the new sum in the first case will be s plus x, and that is not 0. So the new sum again will be not 0, and neither the written number is n. Next, if s plus x were written, then there are two possibilities. The new sum will be 2s plus x with s plus x equals 0. So therefore this will be equal to s, because the other part s plus x goes to 0. And s is not equal to 0. That was our primary assumption. So therefore the new sum will also be not equal to 0. Now the second case is when x equal n. Notice in that case the new sum will be 2s plus n. S, the already written number sum will be s plus s plus x gives us 2s plus n. And this is an odd number because n is an odd number, 2s is an even number, even plus odd will be odd, which is again non-zero. 0 is an even number, so how come odd equals 0? That's not possible. So therefore the new sum is also non-zero. Following this algorithm, Becky can ensure that, for Becky, they can ensure that the new sum, let's say s, sum is now updated to s prime. The initial sum being non-zero shall imply the new sum is also non-zero. Therefore, Becky will not be constrained to write n on the board, because if the sum were 0, then they have to write n. So this is the case that Becky will try to avoid, and this is the case where what Peter will want for Becky to have. So that like they will be compelled to write n on the board. So that is not becoming the case by following this algorithm, and whatever the number they write, you see the number s plus x is equal to 0, which cannot be n, and again if x equal n, they are writing s plus n where s is non-zero, so this is also not n. There are no number n written on the board, and also the new sum is also not getting nullified. This ensures that Becky can evade from writing n on the board cleverly. So this is for n equal to odd, they can evade. For n equal to even, it turns out they cannot. Let's say it's of the form 2k. Now, whatever Becky tries, Peter can constrain and make the sum 0 or make Becky write the number n on the board. Well, how is that possible? So first, as many zeros as required, then Peter claims 2k, so 2k will be written on the board. So this is the claim by Peter, and Becky will write 2k. Now, Peter claims minus 3k. So the process bifurcates. Either Becky can write the number minus 3k after 2k, or Becky can write the sum of 2k and minus 3k instead. So that will be minus k. So these are the two possibilities. Now over here, the sum of numbers equal minus k. Now if Peter claims 2k, Becky will definitely try to avoid writing 2k because n equal 2k. The target for Becky is to not write n as many times as possible, and for Peter to write 2k as many times as possible. So we are trying to build an algorithm for Peter so that Peter will end up with 2k no matter what Becky does. either the sum or the actual number. They will end up with one more 2k starting with some 2k. So if Peter claims 2k, then Becky will write the sum of all the the sum of all previously written numbers with 2k, which is minus k plus 2k, giving us k. So it will be 2k minus 3k comma k. Now the total sum is 0, and if Peter claims 2k, either Becky writes the number 2k or the sum of previously written number, which is 0 plus 2k. Always they are going to write 2k in this step. So therefore, we have achieved our 2k once again through a sum of 0. Now suppose Peter claims minus 2k here, then the process gets bifurcated once again. So let's write it out. Upon claiming minus 2k, Becky can write the number minus 2k, so it will be 2k minus k and minus 2k, or Becky can write the sum of the previously written numbers, which is plus k plus minus 2k, giving us minus k, so it will be 2k minus k minus k. So in this case, notice that the sum equals 0. So therefore, by claiming 2k, Peter will be able to make Becky write the number 2k once again. And over here, the sum of numbers equal minus k, which was equivalent to this case. So once again, claiming a 2k, Becky will be forced to write plus k minus 2k and then plus k. Now the total sum becomes 0. So claiming a 2k, Peter will gain a win because the sum now becomes 0. Therefore, in any scenario, whatever the way Becky follows, Peter will be able to generate one other 2k, and also the new sum in each of these cases equal 2k, and the entire process starts from there once again. And this can be prolonged as many times as required. This can be repeated as many times as required, and therefore Peter will be able to make Becky write 2k 10,000 times or as many times as required. So this works for any event. That is the interesting part. And in fact, this problem occurred in a famous Russian Olympiad, Tournament of Towns. So we have inspired this problem from that one. So I hope you are finding it interesting. There are a lot of such game theoretical problem played between two players. So we ask this in every fortnight worksheet. So we provide worksheets at the doorstep of our subscribers. We provide at least 2 such game theory problems every fortnight. And we also provide a detailed solution 2 weeks later. So they will have 2 weeks of time to submit the solutions online. If you are interested, you can subscribe for a free trial worksheet at www.sumonman.com. We will discuss more such problems soon. Thank you for watching, everyone. Bye.